OK, so we left off talking a little bit about how to encode instructions in a VLIW, or how VLIWs encode instructions. And as you may recall, in a VLIW instruction encoding, you have a very long instruction word. So it could be, I don't know, many, many bytes. So if you go look at something like the multi-flow processors, the multi-flow trace processors, they had very long instruction words. They could, I think, execute something like, in their largest machine configuration, 20-some instructions. And they had to encode this. But one of the challenges was that you didn't necessarily want to have all that encoding space used all the time. So if you are executing a simple instruction or something which doesn't actually need all the encoding space, you end up with a whole lot of no-ops. Or if you have a very long dependency string in your execution trace, if you will, so you have an instruction which is dependent on the next instruction, which is dependent on the next instruction, which is dependent on the next instruction, and you cannot fill any of the extra slots, you're going to end up having a lot of no-ops in your program. So how do we go about solving this? Couple different solutions here. Sidra 5 went off and added a particular instruction, which is a single operation instruction, and used a much smaller amount of memory. So this would effectively reduce your instruction cache pressure. There was compressed formats in memory, so you can hold your instruction sequences in memory, and then when you go and pull it into your instruction cache, it would expand to the fully expanded version. And this is kind of like a compression algorithm. You're basically compressing your VLIW instruction sequences, because otherwise these things are very, very large and have lots and lots of zeros or no-ops in them, because the probability you're going to fill sort of 20 instructions per cycle is low, but you want that capability there in case you actually do want to execute 20 instructions per cycle. Another solution here is what's actually used in the Intel Itanium or IA64 processor line, and also the TI DSPs, the C6000 series. They have the ability to effectively mark where a bundle starts and stops. So it's something sort of between a variable length instruction and a fixed format VLIW instruction. So we'll talk more later in today's class about how IA64 or Intel's Itanium handles this. But roughly what happens is they have a fixed instruction format, and you can fit sort of 3 instructions per bundle, or what they call a bundle. And then if you want to go over that, you can keep going over that. And they have special bits in their instruction which says, oh, well, this is going to express some more parallelism later. So you need to look at the next bundle and try to fetch that bundle, and that's all can be executed parallel. So it's still a parallel execution semantics, but the formats are not necessarily fixed. And this is sort of outside the bound of classical VLIW. Now it's going into a little bit more modified VLIWs or more contemporary VLIWs. So today we're going to, as I said, talk about how to go about getting all the performance that out-of-order superscalars can get, but in the context of a VLIW. So we're going to slowly build up all the different techniques that out-of-order superscalars have and all the ways that they can get instruction level parallelism, and then apply that inside of VLIW, or how we make small changes to classical VLIWs to get a lot of the performance back. OK, so let's talk about the first trick here. One of the questions that comes up, or the problems that comes up here, is if you have branches and they mispredict, this can limit your instruction level parallelism in a VLIW. OK, so why is this worse than in a out-of-order superscalar? Well, an out-of-order superscalar can dynamically schedule around branch mispredicts. So if you branch mispredict, you can basically schedule other code or speculatively schedule code depending on your prediction. But on something like a VLIW processor, that's a lot harder to do because you don't have a dynamic scheduling engine behind there. The compiler had to go do all that scheduling statically at compile time. So how do we go about fixing this? Well, one solution is just to eliminate all the hard to predict branches. So you take out the branches that might be hard to predict. So your branch predictor is trying really hard. you could still have a branch predictor in your VLIW processor, but some of these things you don't know. It's like a data-dependent branch. How do you know which way it's going to go? And this is a problem even for superscalars, but at least in a superscalar, you can try to sort of backfill instructions or try to do something or move around, if you will, loads or long latency instructions around branches. So in an out-of-order superscalar, you can potentially move a load beyond a branch. But in a VLIW processor, that's not easy to do because the compiler has to make that decision whether that branch is going to predict taken or not taken. And that may change over the lifetime of the program. And it may also change as the depending on the sort of input sets to the program. So it may not be something that's compiler time even knowable. OK, so our first technique here that we're going to use is called predication. So let's define what predication is. Well, first of all, predication is a technique that allows you to basically change the result of a register based on some other register. And it's going to let us transform hard-to-predict branches into data flow or data dependencies. So we're going to add something to our instruction set, and it's going to take what looks like a small branch or a short distance branch, and we're going to basically execute both sides of those branches, or the taken and the non-taken code path, and then at the end, decide which one was the right one with something like a select operator from C. So this is like the question mark colon operator, which no one ever uses in C. This is sort of the equivalent of that, but we're going to do it in one instruction, or maybe two instructions. So let's take a look at how this helps with small branch regions or branches which are hard to predict. So we're going to introduce two instructions. And I also want to point out that predication sometimes shows up in superscalars, processors, or sequential instruction sets also. So a good example of this is two instructions very similar to this are actually in x86. They're called cmove, or conditional move. And we're going to introduce conditional move as the most basic form of predication. So let's look at the semantics of these two instructions we add for conditional move. First instruction here, move 0. So what does move 0 do? Well, move 0 tests whether one of these input operands here, RT, is equal to 0. And if it's equal to 0, it's going to move RS into the result register, or the destination register here. So it's going to move RS into RT, or RS into RD if RT is equal to 0. And if RT is not equal to 0, it's just going to leave RD alone. OK, well, on first appearances, that seems like a very simple instruction. It's basically just doing a copy operation. It's a gated copy. It looks a lot simpler than something like add or subtract. We don't have to do any math, at least. There's no compare. I mean, the compare is easy. It's just the equals. It's not a less than equals. So it's a pretty simple instruction. And we're also going to introduce move not 0. So it's kind of the complementary one of this. And we're going to want this because when we go to execute code, we're going to want to, let's say, have an if, then, else. And we're going to want to execute the then and the else at the same time, or roughly at the same time, or indiscriminately, not dependent on the branch. And at the end, we're going to decide which one was the correct one. And we need sort of two instructions here to choose, well, was the positive one the right one, or the one where the conditional value is true or false the right one, or the one where it was true, or vice versa. So move not 0. Move not 0 is going to do the same thing here. It's going to see, except the sense of the condition code is going to be different. It's going to sense if RT is not equal to 0. And if RT is not equal to 0, then RS is going to go into RD. Else, we're just going to leave RD alone with the original value of RD. OK, so let's walk through a quick code example here. and see how this helps. So here we have a code example. We have some C code. We have non-predicated MIPS-like assembly code. And then we have a MIPS-like assembly code here with these fancy 2 predication instructions. And all 3 of these are doing the same thing. So let's look at this piece of code here in the C code. It's probably the easiest to understand. It's going to start off, and it's going to say if A is less than B, so there's a condition, and then there's a then and an else. So what does this actually implement? Well, this is a minimization function, or a min function. X gets the minimum of A or B. If A is less than B, it gets A. If A is greater than B, it gets B. So it's going to assign to X the smallest value of A and B. And these sort of if-then-else's, you can see here it's pretty short. We don't have a whole lot of code in either the then case or the else case. And that's going to be important in a second. You'll see why. Mainly it revolves around if you have lots and lots of code, or one of the sides of the branches is long, it may not make sense to actually predicate this, because there's some cost to predication. OK, so here's some assembly code, does a similar sort of thing. Set less than, this is a comparison operation in MIPS. So we're going to do set less than, and these are going to be R2 and R3 are going to have our 2 A and B values here. If it's less than, we're going to put it into R1. If not, this gets set to 1 or 0. And then we have a branch 0 here, effectively. What is this? This is a branch. OK, it's a branch equal with 0. It's a little odd. We probably should have just put branch 0 there instead. But it's going to check to see whether this value is 0 or 1. And if it's the one direction, it's going to jump to L1. If it's the other direction, it's going to fall through and then jump over this move. And these 2 moves here are the 2 assignment operators, the x equaling A or x equaling B. OK, that's not so bad. Let's analyze how long this takes, how many cycles this will take to execute on a sequential machine. OK, it does this set less than. It's 1. It does this branch. So that's 2. Let's say the branch is not taken or falls through. 3, 4, and then the jump over. So it's going to be 1, 2, 3 instructions in the one. Is that right? 1, 2, 3, 4 instructions in the one case. And the other case, it's going to take the branch and jump to here. So it's going to be 1, 2, jump over all this stuff, 3 instructions. OK, that's not so bad. So the one case is 4 and the other case is 3. They're different. Now, something else that makes this interesting is, let's say this branch is mispredicted. It's a data-dependent branch, A and B. So what's a good thing to predict here? Can our branch predictor do a good job on this? I don't know. Depends on what you know about A and B. If the compiler knows nothing, or the hardware knows nothing, you're not going to be able to do a particularly great job. So let's say it's a data-dependent branch, and it's 50% the one direction and 50% the other direction. Is this going to slow down our execution? Well, sure. It's going to slow down our execution because all of a sudden, when we take a branch, one of the directions, whichever way we predict, the mispredict path is going to add some mispredict penalty. So instead of the one path being 3 and the other path being 4, let's say the branch is predicted, I don't know. Let's say the branch is predicted not taken. So it predicts the fall-through case. So all of a sudden, the fall-through case is going to be 1, 2, 3, 4 instructions. And let's say we have a 2-cycle branch mispredict penalty. So let's look at the other case. So the other case is going to be 1, 2, and then 2 cycles of mispredict. So that gets us up to 4. We're going to branch over 5. So it's going to be 5 cycles. So all of a sudden, we have our branch mispredict penalty coming into the equation here of And two-cycle branch mispredict is relatively benign. If that starts to grow longer, then you really start to have problems with this. OK, so let's take this code sequence and look about how to predicate it. So if we're going to go predicate this, we're actually going to execute both sides regardless of the value of the if clause or the conditional clause here. So if we look what we do, we actually have restructured the code here a little bit. And this is our compare. This is our if still up here. We have a set less than. And then we say if R1 is 0, move R2 to R4. Else, just leave it alone. And then here, if R1 is not 0, move R3 to R4. And what's important to note here is this non-destructive operation, especially here in this last instruction, is really important. Because if the move 0 was executed and that copied a new value into R4, and then this move not 0 were to somehow change R4, you lose that result from this previous one. So this really depends on these operations being non-destructive if their condition is not true. OK, so let's analyze this from a number of instructions perspective. First question is, does this matter what happens to the branch or what happens to the condition? Is it going to have different numbers of instructions or different numbers of cycles dependent on the direction of the condition? Well, no, there's no branch. Nothing's going to change. So in all cases, this is just going to take 3 cycles. So all of a sudden, we transform something which can take, as I said, if let's say you have a branch mispredict penalty, 4 cycles or 5 cycles. So on average, let's say the branch is taking 50% of the time either direction. We'll split the difference there, and we'll call it 4.5 cycles on average. And we've turned it into something which takes 3. Well, that's a great win. So where else is this useful? Does you always need to have if, then, else clauses to make this work out? So no. This also works good for small code hammocks. So I say a small code hammock is just a if which jumps around a small piece of code. And if you can't predict that if very well, then it makes sense just to go execute effectively what's inside that code hammock, or that small piece of code, always. If, for instance, you have 2 instructions inside of a code hammock, and your mispredict penalty is like 10 cycles, and you don't know whether the branch is being taken 50% of the time either way, all of a sudden, your average mispredict penalty is going to be something like 5 cycles. You could have just executed the code in the middle. It would have been faster. You could have executed the 2 instructions and then just done a conditional move at the end, and that would have been basically always better. OK, so we bring up some questions here. What if the if, then, else has lots of instructions? So let's say we have if, then, else here, but there's 1,000 instructions here and 1,000 instructions there. Should we predicate this? Let's say the branch mispredict penalty, as I said, it's 10 cycles, and it's 50% either way. But there's 1,000 instructions in the if, the then clause and the else clause. Well, no, that would never make sense to do, because you're basically doubling your code, and if there's a lot of code there, you'd be better served by just doing the branch, because you'd be taking something that was could be 1,000 instructions and turning it into always 2,000 instructions, or doubling the number of instructions executing, versus just adding, let's say, 10 cycles of branch mispredict penalty, or an average 5 cycles of branch mispredict penalty to your 1,000 that you have to execute. So all of a sudden, you're adding a little overhead. So where this predication really helps is for small pieces of code where you don't necessarily know the branch outcome, or can't predict the branch outcome very well. OK, what if the code is unbalanced? So you have an if, then, and an else. But the then clause and the else clause are very different in size. So one is 3 instructions, and the other is 1,000 instructions. Does this make sense? Well, it goes back to the same argument we had before with the very large if, then, else clauses. If the code is really unbalanced, you have a lot in the then clause and a little bit in the else clause or something like that. And let's say the branch is taken 50% of the time, it might make sense just to use an actual branch there and deal with the mispredict penalty costs versus trying to somehow predicate it. Because in effect, what's going to happen is, let's say you have 3 instructions and 1,000 instructions on the 2 different sides. You're going to be executing, if you predicate, 1,003 instructions every single execution time, plus maybe some sort of conditional moves at the end, some overhead involved. Versus if you have 50-50, and you have to add a little bit of a branch overhead penalty, your 50-50 chance is going to say, well, I'm taking 1,000 plus 3, and I'm going to add those 2 things together and take the average of them, basically. So it's going to be, what's the average of that? It's going to be like 501 or something like that, or 502 cycles. And that's going to be better than always executing 1,000 cycles. Let's see, anything else we wanted to say here? Yeah, one last thing I wanted to say here before we move off this slide. Move 0 and move not 0, or sometimes called cmove, conditional move instructions, are what are called partial predication. And we're now going to move on to full predication, where we can actually put conditions on every single instruction in our register, every single instruction in our ISA. But this is a little bit easier to do than full predication. This is sort of the first step that people typically implement, and it's called partial predication. And just to hammer this home one more time, predication is really turning what was control flow into a data flow operation or a data operation. OK, so let's take a look at full predication. Full predication, we're actually going to change the instruction set such that all of the instructions can be, or almost all the instructions are executed conditionally based on some predicate. If the predicate is false, the instruction is not going to do anything. It's just not going to have any side effect. So let's look at a code sequence here. So in this code sequence, we have an if, then, and an else, and then some code after we're done. So here we have if. A little bit different. This is not actually in MIPS code. This is something, just sort of pseudocode here. But it's going to say, this is our if here. If A is equal to B, then branch to B2, else fall through. Here we're going to execute our else clause. And when we're done, we're going to branch over the then clause. So not anything interesting here. 4 basic blocks. I don't know if we've introduced this term yet in this class, but I wanted to introduce the term basic block. Basic block is a piece of code which has strictly one exit point and one entry point. So you could enter it from other places. You can jump to it from other pieces of code. But once you enter the piece of code, you're going to execute the code all the way to the end, and then there's one place you can leave. So you can either jump to someplace else or branch, and you can fall out to 2 different places. But the exit point is only one place. So what we're going to make the differentiation here is the piece of code can have, for instance, 2 branches. That's not called a basic block. That's called a bigger type of block. But this is a compiler term. And it's just good to know. OK, so let's apply full predication here. So these are relatively short code hammocks. 2 instructions here, 2 instructions there, and 2 instructions in the else, 2 instructions in the then clause. This looks like a really great place to think about predicating. OK, so let's take a look at the predication here. And I want, before we do that, I wanted to just say that one of the big reasons that we're trying to predicate on a VLIW in particular is in a VLIW, we have lots of extra, or we could potentially have extra parallel execution slots. So in our instruction sequence, or instruction encoding, we have extra places to put code. So it may not actually hurt us to predicate. Because a lot of times when we go to predicate, we're basically going to execute both sides of the if, then, and else. And it's bad if we have to execute both sides of the if, then, and else, and they're big sequentially. But if you try to sort of slide them up next to each other, if you have extra no-op slots or extra slots in your VLIW, you can actually decrease the critical path through your program. So let's look at this. And we're actually going to do this in this example. So in this example here, we took this piece of code and added full predication. So when we say full predication, we added some extra things to these instructions. They look a little strange at first. So here we have instruction 3, instruction 4, instruction 5, instruction 6. And these are the same ones that were back over here. But instead, we added some extra words in front of them here, or these parentheses with P's in front of it. What that is these are predicate registers. So we're going to add a second register file into our processor where we can store effectively 1-bit values, sort of true or false values, that are going to determine whether this instruction executes or doesn't execute. Excuse me. So what this means is if P1 is 1, execute this. If P1 is 0, nullify this instruction 3 here. And we have a double pipe here. What am I trying to show with this? Well, I'm trying to show that this is parallel. This and this are executing at the same time. Because we have a very long instruction word processor, we can execute multiple things at the same time. And what we've done here is we've actually slid this up next to the then up next to the else. And we're going to execute them at the same time, dependent on these predicates. So this is the else block, and this is the then block. We're going to execute concurrently. OK. Sort of stuff before the if, stuff after the if, then, else is all done. That's sort of from that 4 basic block example. What's this instruction? This instruction has very interesting semantics. And this is something that you probably have to add if you're going to try to have full predication. OK, so it's a compare. So this is our comparison. If A is equal to B, and then it writes into 2 outputs. Ooh, that looks broken. That looks wrong somehow. How can we have one instruction write to 2 things? And what is the semantics of it? What does it write to here and here? Well, what this is actually doing is this is writing the positive outcome of this compare to the one, and the inverse, or the negation of that, to the other. And this is useful because then we can go use these predicates down here. We can use the positive one, let's say the negative one, and that can drive whether we execute the sort of else clause or the then clause. So lots of instruction sets that have full predication have either something like this. This is one option. You can actually have sort of 2 outputs, and you load 2 predicate registers. The other option is when you go to actually encode the instructions, you have sort of a not bit. So it denotes the predicate register. But when we denote the predicate register, we also denote whether we take the predicate register being true or the predicate register being false as what drives whether the instruction executes in our full predication scheme. So in effect, this is computing P and P bar at the same time and running them 2 different registers. And then we can use those separately down here. And interesting result here in ISCA 95, Scott Melke showed that you can, on average, let's say, remove 50% of your branches by using full predication. Now, full predication is not easy to build. Very few instruction sets have actually had full predication. Itanium was probably the closest to a real processor that was built that has almost full predication. It doesn't have quite full predication. The HP Plato instruction set, I think, actually had full predication. I think this is what Scott Malky was working with, or a derivative of that. So you can actually have instruction sets that people have thought about that have had full predication, but not all things are easy. So first thing, you need to add an extra register file for the predicates. You need to bypass those predicates. You need to compute them. There's some overheads involved, and we're going to talk a little bit more about that.